this one became quite famous, is sometimes known as the names in boxes problem. In this problem, there are 100 prisoners, and the warden comes and tells them that they will be given their freedom if they can win the following game. 100 boxes are going to be put on a table. In each box will be put one of the prisoners' names on a piece of paper. And they'll be lined up on a table in a room. And the prisoners will be brought into the room one by one. And each prisoner is permitted to look in 50 boxes, trying to find his own name. When he's done, he's escorted out of the room. He must leave the room exactly as he found it, and he has no further communication with the other prisoners. In order to win the game, every prisoner must find his own name. Okay? Now, this sounds really completely hopeless.
Wait, so just say again, so how many prisoners and how many boxes?
There's 100 prisoners.
100 prisoners.
100 boxes.
100
one name
boxes.
in each box.
Oh, you can only look in 50 of the 100.
But each prisoner can only look in 50. So any individual prisoner's probability of finding his own name is 50%. Is 50%. Half. Nothing you can do about that. Okay? So how do you do this? I mean, what's your algorithm, right? Well, one possibility is everybody looks in a random 50 boxes, right? That gives your probability of winning the game 2 to the minus 100. Not very good. Another algorithm is everybody looks in the same 50 boxes.
That has a probability of success of 0.
Right, which is essentially the same as the first
one. Indistinguishable. All right, fair enough.
So the story with this puzzle is that Peter Broh-Milterson and Anna Gall, two theoretical computer scientists that you may know, were working on a problem, and they needed to be able to show that in a certain version of this problem, that the prisoners had no algorithm which would give them any decent probability, 1 over polynomial in n or anything like that. And but they didn't see how to prove it. And one day, Milterson happened to be passing the problem on to a friend of his, Sven Skyhem, over lunch. And Sven Skyhem said, "Well, have you tried this?" And Milterson told me he fell off his chair. Okay, so it turns out that there's an algorithm which will guarantee the prisoners a better than 30% chance to win the game, irrespective of what n is here. It works for 100 prisoners, but also for 1,000,000 prisoners, the probability of winning is better than 30%. And and even after you see the solution, it's hard to believe that this really works. And remember, every individual prisoner has probability only 50%. Right? There's no communication. So how could you possibly get enough correlation into this problem to have their probability of all of them finding their own names be 30%? It's ridiculous. But here's the algorithm. That's absolutely wonderful. The prisoners first assign ownership of the 100 boxes randomly. In other words, they choose a random permutation of the boxes. They assign ownership of the boxes, and every prisoner gets to know all the ownership, gets to memorize all the ownerships and everything. Of course, these ownerships may have nothing to do with the names that are inside the boxes, but that's okay. Yeah. So now prisoner A goes into the room, and he opens his box. He opens the box that's been assigned to prisoner A. He looks inside, and it's got some other prisoner's name in it, maybe prisoner G. So then he goes over and he looks in prisoner G's box, and maybe prisoner Q is there. Then he opens the box for prisoner Q, opens it and finds prisoner C there, etc. He keeps doing this, and he's hoping that he'll find his own name. If he doesn't, too bad. And then he leaves the room. and the next prisoner does exactly the same thing. Next prisoner B goes in, he opens the box for prisoner B, looks at the name inside, opens that box, and hopes that eventually he'll get back to his own, to his name. So that's the algorithm, right? Well, why in the world should this work, right? What's going on here?
Right, and why would this be better than, for example, just going through in their permutation order or something like that?
Yeah, I mean, it's not at first at all clear why this would work. In fact, the only way I know people come up with this algorithm is they're looking for something for prisoners to do, and the problem is once you think of this algorithm to not dismiss it, but instead to think about what would make it work. So what's going on here is that this random permutation, combined with the permutation of the prisoners' names in the boxes, gives you a permutation of the prisoners, which is a uniformly random permutation. Okay? So the permutation is defined in the following way. You take a prisoner, you look inside his box, you see whose name is there. That defines the permutation. So I said that prisoner A's box contained the name of prisoner G. That means that in this permutation, A goes to G. Okay. So what's going to happen is that prisoner A will find his own name if in this permutation, the cycle that his name is in, the cycle that A is in, has length at most 50. If that cycle has length less than 50, or to 50 or less, he comes back and finds his own name. Otherwise, he doesn't. So what does that mean? Well, that means that the prisoners will actually win this game if there are no long cycles. Because then everybody will start in their own cycle, come back around, and find their own name. Okay? Now, it turns out that it's actually very easy to compute the probability that a permutation contains a long cycle.
Wait, hang on 1 second though. So, but not only short, but it has to be short and contain that prisoner's information, that prisoner's name. Right?
Well, now we know it contains that prisoner's name because he starts at the box that he owns. So, for example, suppose the cycle is A, G, C, A.
Oh, the only way to get back to it is if you found the name.
That's right.
Ah, okay. All right. So now your next step was you can
So
bound the probability
next
that
step
there's
is just
long
to
cycles.
compute the probability that a random permutation contains a long cycle. Well, it's actually quite easy to show. It's just a little, just write down the binomial coefficients. That the probability that a permutation contains a cycle of length k, where k is bigger than n over 2, is exactly 1 over k. So the probability that our permutation contains a cycle of length greater than 50 is 1 over 51 plus 1 over 52 plus 1 over 53, et cetera, plus 1 over 100, which is about natural log of 2.69 something. So the probability of the prisoners winning is about 0.31. You know, you can sit and stare at this thing and still not really understand why it works so well.
That's crazy. So it's got harmonic numbers in it and logarithms and a simple kind of tail chasing kind of algorithm. But
That's right. It's just nice reasoning, right? Nice undergraduate reasoning.